ER4120, Computational Mechanics, Module Introduction, and I'm Dr. J. Whitty. A recap on the fundamental theorem of algebra. This is critical, indeed fundamental, to solving interpolation problems and the vast majority of those found in Newtonian mechanics, fluid flow, heat transfer, aka computational mechanics. The theorem says that for an nth degree polynomial, that is to say, namely a polynomial that can be written as a power series where m goes from 0 to n, so in this type of form, a0 x to the 0 is 1, of course, a1 x to the 1, a2 x to the 2, etc., has n distinct roots, rk, though these may be repeated or occur in conjugate complex pairs. A corollary of the fundamental theorem of algebra is the factor theorem, which harps back to your pre-degree work. If rk is a root of the polynomial p of x, then x minus rk is a factor of the same polynomial. And we say that p of x can be written as r0, x minus r0 multiplied by x minus r minus x, and so forth. That is to say, the probability of x, so the polynomial x is equal to this summand, which can also be written as the product of x minus each of the roots. A corollary, roots relations, a further inference for each of these theorems provides a relationship between the roots and the coefficients. So for the given polynomial, then the sum of the roots is always given by minus 1 to the k, ak over an, as you probably found from your pre-degree work, finding the roots. This can be used to find the roots of the equation. So as an example, we want to solve the cubic equation x cubed 8 to the minus x squared 9x plus 8 is equal to 0. And this particular example is from Stroud's Advanced Engineering Mathematics text. There are computational methods that can be exploited to generate a set of the non-linear equations. So in the first instance, what we would do is just apply the corollary minus 1 to the k, ak, in which to generate each of the equations. So here we'd say r1 plus r2 plus r3 would be 8 minus 1 to the 1 multiplied by 8 divided by 1 in this case, so minus 8. And then we take the product of each of the roots, so we'd say r1 times r2, r1 times r3, r2 minus r3 would equal minus 1 plus 9 divided by 1. And then we've got plus 18 divided by 1. But this time it's r1 times r2 times r3. This generates the three equations, which an iterative nonlinear equation solver such as ease, this is a triviality. So we would set these up in the as a set of solutions in the ease software. R1, R2, notice the brackets, will equal this, R1 times R2, etc. So just literally rewriting the equations. An alternative method would be to use the Maxima software, which will calculate these things out algebraically, and again it's just a matter of writing these in the correct form and then issuing the solve command. So in Maxima we would just say equation 1 is, equation 2 is, equation 3 is, and then solve that accordingly. So Other computational solutions, other codes are of course available to solve nonlinear equations. These include Scilab, MATLAB and Python. Python will be the language of choice used throughout this module of computational mechanics. So one way in Scilab is to simply define the function, define it as a multiple function. So we define equations as equations of R, where R is just the set of equations, and then we would solve these set of equations given the fsolve command and a set of initial guesses. In Python, very, very similar. We would need, first of all, from the more about Skippy later, the scientific Python optimize, we would need to import the fsolve from that particular library before we use it, and then we set up equations as known as a lambda, which is again this, analogous to the define, an inline function, which is the inline function is a function of R, and after the colon we put these in as we would make these a set of a list with an equation in each of in each list. Again, R0, R1, R2, noticing that in Python we do have to start from 0, as thankfully it's a zeroth order, starts from 0 in its array. Each of the arrays will start from 0. In MATLAB, very similar way in which it does, but instead of using the anomalous lambda function, it uses this at symbol. So equations at R, and then we just simply write the equations. Don't forget, of course, in MATLAB and Scilab, you will need the dot command if you're going over each of the lines accordingly. All of these methods, when used, will render -1, 3 and 6 respectively. So it's just a matter of copy and pasting those into the required codes, and we'll do this when we look in more detail in the workshop sessions. So a little bit more on the roots of polynomials. Each of the codes can be used to find the roots, all the roots of the and the nearest one. So from Skippy we have optimize and import fsolve. We could say fp is the lambda is the functional polynomial, I guess, is a lambda, and this is the exact polynomial, and then we could just ask fsolve to find a root near to the root nearest to 2.5. In Maxima, it's simply a matter of setting up the equation equal to 0 and saying find root of equation using equation 1 of x between the values of 1 and 5, as it will use a bisection type method. More on that as we move later on in this particular video lecture. In Scilab, it's a matter of defining using the def command, setting up the equation and then asking to solve that equation near 2.5, for instance. And almost identical, instead of the def, we just use an anomalous function at x and ask MATLAB to solve fp near 2.5. There is also the roots command. So the roots command should find all the roots rather than just the nearest one. So if in Python this is from numpy polynomial.polynomial, that's just where it's located within the numpy library, we import polyroots, and then we simply provide the zeroth, the constant, that's right, the constant, then the x, and then -8 for the square, and so it's in the order as we would write down the polynomial from the 0th up until the x to the 0 up until x to the n in this particular case. Polyroots will find all the necessary roots of that particular equation. All roots is available also in Maxima, and if it cannot find those algebraically, it will resolve to a Newton-Raphson solver. This is x cubed 8, just simply write the equation in and then ask for the roots. Maxima, very, very simple. Poly 0 of x, to say that x is a polynomial variable, then just ask for the roots of the particular polynomial verbatim. And with MATLAB, it's the opposite way of Python. We put x cubed first, minus 898. So it's of importance to read the accompanying help files to be able to formulate these for each of to be able to find the roots of these polynomials, and these will be of use moving forward for the vast majority of computational mechanics type activities. So on to the teaching and learning philosophies. The module was roughly divided into 3 parts. The mathematical principles, in particular the solution of ordinary differential equations, followed by solutions of partial differential equations, and these are interdispersed with research-informed case studies, so applications of these particular methods to research which is ongoing within the John Tyndall Institute. Teaching comprises of online lectures of 2 hours per week, virtual seminars through Microsoft Teams for 2 hours a week, and modelling tutorials. We've blocked out 4 hours for the virtual sessions, but an hour of this will be taken up usually by questions and sorting out any technological problems that may occur. Additionally, there'll be self-study, coding and tutorials will be required about 2 hours a week, assessment preparation probably about 2 hours a week, and revision and recitation for the 2 major tests, that is to say the midterm in January and the online final on the 21st of May, penciled in for the 21st of May at the moment, subject to change of course. The revision and recitation will require at least 15 hours to obtain a pass grade in those assessments. If higher grades are required, then it's usually about an extra 15 hours per grade. So if you wanted a merit, then you'd be looking at 30 hours, maybe 45 to 50 hours revision and recitation to ensure that you get a distinction grade or a first class grade. The assessments, there will be fortnightly worksheets which will be you'll be afforded opportunities within the virtual seminars and modelling tutorials to work on those worksheets, and be provided all the skills to solve the problems throughout. Then the solutions will pop up every Friday, so every second Friday, fortnightly. The midterm milestone test will be on the 15th of January, that's the last week of the university's first testing week. There's an assessment for learning which will begin in November, and the handing date is in February. More on the assessment for learning strategy as we move into that particular part of the module. And the final online exam is, as I said, the 21st of May. Just an overview now of the particular topics. The mathematical fundamentals, together with the first research-informed case study, is part of the course we presented over the first semester, and the first research informed case study also will formulate part of, or the vast majority of, I should say, the assignment. So we kick off with numerical calculus. In particular, we look at interpolation and extrapolation this week, differentiation next week, and integration the week after. And then we're into the modelling of ODEs, so first order, higher order, transform methods and non-linear ODEs. Each of those, all but the transforms, taking a week apiece, with the transform methods taking 2 weeks. And then finally we have an examination release on week 11, and we'll look at friction heating and Fourier analysis to take us up to the end of semester 1, 3 weeks on that. So the learning objectives for this particular session is to recall solutions to linear equations using matrix methods. We need to describe and discuss the differences between interpolation and extrapolation problems. Solve nonlinear equations using a variety of appropriate computational methods, and we started that in the recap, of course. Use computational tools to perform interpolation on realistic data sets, hence evaluate engineering systems using vectors and matrices. And we'll see that once we're able to use the interpolation problem. So interpolation, just to remind you of that, is if we have points, a set of data points, then how do we fit these data points? What's going on in between them, and how do we approximate them? Well, the easiest approximation is just to approximate with straight lines. This has the advantage of being simplistic, but the disadvantage that has no smoothness at the points, and therefore doesn't have a derivative at the actual interpolation points. So there are other methods, Lagrange and splines, and we'll be looking at those in a little bit more detail as we move through. The codes, the major codes used for these sessions will be Maxima and, of course, the Mighty Python. So the structure of these video lecture components are subdivided into 4 bite-sized parts. The first is the introductory material, which will cover any recap and points of order raised in the discussion forums. Introduce, in this case, the concept of interpolation. We'll then look at concepts and principles such as linear interpolation, Lagrange interpolation and splines. Thereafter, look at some examples, in particular the principles of least squares and elasticity. Finally, the final part is dedicated to summary and feedback, where we'll point you to the final learning survey, which we would hope you would be able to fill out each Friday afternoon. Just as a point of order, the information in the module space of our virtual learning environment contains a week-by-week breakdown of the module, including all the formative and summative assessments. On software should be used extensively throughout the module delivery, and most notably we'll be using open source software, the Python universe, but with particular emphasis on SciPy, NumPy and Matplotlib. This can be obtained by clicking on the module information in the Blackboard virtual learning environment. We will touch on the use, as we have done already in this particular lecture, Scilab, Ease, MATLAB, but extensively we'll also use Maxima, open source computer algebraic system. There will be also the use of ANSYS Workbench, possibly ANSYS AIM, and most certainly 3D Experience. So to introduce the problem, a problem that you've probably came across in your pre-university mathematics, we are to compute the square root of 7. A triviality these days with the power of computers, but a very informative problem to solve, to see how the computer goes about solving problems of this type. Iteration is generally used for this. This is a process of effectively finding closer solutions from previous approximations, and it may use some form of interpolation, but probably not extrapolation. Interpolation is concerned with the approximation of values between discrete data points. So for instance, we have 3 different types of interpolation between these points. They fit the points exactly, which is always a telltale sign of an interpolation scheme being used. If a linear interpolation was used, you would, and you were trying to calculate somewhere in the middle of these 2 points, then you'd get very different values, as we will see, depending on the interpolation scheme used. On the other hand, extrapolation is trying to find values outside the range. So if the data points are the data points shown, then extrapolation is concerned with finding values outside the data points. And again, if we was to extrapolate outside, we would get very different values depending on the interpolation scheme. Of course, it's not recommended to extrapolate outside an interpolation scheme for obvious reasons, and the further you get away from the data, the confines of the data points, the less accurate and the final results would be. So again, the concept of iteration, there's a huge amount of these methods used to solve both linear and nonlinear equations. We'll begin there with the systems of linear equations, including the Gauss-Seidel linear systems, secant method, and then move on to the very powerful Newton-Raphson method. Essentially, one starts with an approximation, starts an incrementation, it's then computed, improved. We then say, is the solution less than a particular tolerance? If the answer is yes, then we do the next increment. If it's no, we'll then go and change our criteria, our value again, to get a closer approximation for each solution that we need to find. So in a graphical method, this is kind of the secant method. What we would do is we would first say, well, we've got a value close, f of x, which is close to, let's say, the root of the problem, and one way of doing that would be to solve the problem between 2 variables, say x1 and x0, and as long as we've crossed the root, that is to say we've got a positive value for our function of x and a positive value for our function of x, say at x1, and a negative value, say at x0, we know the solution somewhere in between that, and then we would use a scheme to approximate and get nearer and nearer values to the root, which is about here. And as you can see, if we was to reduce this to x2, we'd get closer to this particular root, and hopefully at the end of a number of iterations we get as close as possible to the specific root. That's not to say that with the power of computational methods that the first thing to do to find that approximation would simply be to plot the graph, and we'll show you how to do that. There are other schemes. This particular scheme is the Newton-Raphson scheme. The Newton-Raphson scheme uses the derivative, the analytic derivative or a numerical derivative, in which to approximate the next solution. And as you can see from this, it would find the gradient, move down that gradient to find the next solution, plug that solution into the function, and then do it again. Obviously, you can see from the two graphs here, the two cartoons, that the Newton-Raphson procedure, if it does converge, would converge much quicker than this procedure, which is the secant. Starting again with systems of linear equations, the standard method of solution for such systems of equations would be what's known as Gaussian elimination, and it is it solves equations, though can become unwieldy when you look at large systems. So this is why we can use iterative methods. In fact, some of the iterative methods are quicker than solving analytically, especially in a computer. And Gauss-Seidel is an example of this. So for example, we have three equations here. I've used x1, x2 and x3. This could quite easily be x, y and z if you're more comfortable with that. We tend to use x, y, x1, x2 and x3 because they're very easy then to represent these as vectors. And one of the, going back to the learning outcomes of the module, one of those learning outcomes is to model systems using vectors and matrices, and we'll be starting in this video lecture. The process is to solve each of the equations for the first equation for x1, the second equation for x2 and the third equation for x3, and use that as successive iterations into each one. So in this particular example, we take the 3 across, and we take the so the 3x2 across becomes negative, the 5x3 across becomes positive, and then we'd say x1 of n equals x2 of n minus 1, whatever the initial guess was, x3 of n minus 1. Then we solve the next equation for x2. Now, because we have an approximation for x1, we'll use this in this approximation. So here, this is 28 minus x1, which we already have an approximation for above, and then we take the minus 3x3 and of course divide by 5, and this would give us the approximation for x2. We've still got x3n minus 1, so we're using the previous one, but now the new computed one, which shows you that you should get a faster solution using this iterative method for large sets of equations. And likewise for x3, we would leave x3 by itself momentarily, take x1 across, becomes minus, but we'd use this approximation, and then we take this the 7 across, and we'll use this approximation. Okay, so two methods. The first method I'm going to solve using Python, and then we compare this with the values using Maxima and introducing a loop in Maxima to you for the first time. In Python, again, we need to introduce the concept of a loop in Python. The first thing to do is set up your initial guesses, and the initial guesses are x1, x2 and x3, and then I've said x vals are equal to this value of x. N is in range, so n is the number in the range 1 to 6, 0 to 6 I should say, so 0, 1, 2, 3, 4, 5, and I've used x0, x1 and x2. So the xvals is to set up a list where we can append this list, and you can see this append down here, so you can see the iterative nature of the solution. And then I've simply put these equations in verbatim with the added caveat that we reduce the value of so 1 becomes 0, 2 becomes 1, and 3 becomes 2 because of the zero indexing notation required by the Python language. Thereafter, it's literally just a matter of computing these equations verbatim, so writing them out as in Python script. So it's 1 minus 3x1, 5 minus, so we'll use these, and then cleverly we've used x0 in the next computation, and then we've used x0 and x1 in the final computation to get the new value of x, x0, x1, x1, and then we'll print it. Thereafter, in xvals, we're just appending this, so it will put the next set of solutions next to it, so we can then view it in the Spider environment. In Maxima, first thing to note is do tell Maxima that these are floats, and the way in which you do that in Maxima, because Maxima is an algebraic solving system, so you have x 1.0, 1.0, 1.0 to say that these are floating point representations, and then again xvals is simply a list. Notice here equals means something very specific. In Maxima it means you're setting up an equation, so you have to say x assumes the value, so is these particular values for this computation. We've gone 1 through 10 do, and that do needs to be in a loop, so we'll start the do there, end the do that loop there. The only difference here now is that x1 is computed here, x2 is computed there, x3 is computed here in exactly the same manner as we would in Python. The only caveat being is that we have actually used the values in the list x1, x2, x3, so there's no reason to overwrite those any longer. And then we just say xvals, we append xvals with this new value of it, so this is the append routine. So the syntax slightly different. I think it's a little bit easier to see in this particular case in Python than it is in Maxima, but it's completely up to you on how it's implemented. Okay, implementations for MATLAB, Scilab users and ease. The Gauss-Seidel method can be implemented in ease, MATLAB or Scilab specifically. Again, we just pop these equations in. It's relatively straightforward to do that. If you run those in MATLAB or Scilab, you'll get the same result. Little bit more complicated to do this in ease. Not that much complicated, but it is a little bit more because we got the duplicate command. So x1 is set, x2 is set, and x3 is set explicitly I should say, and then we duplicate from 1 to 6. x1, x2, x3 are then computed from the formulae we just derived, and then we have an xvals which we just update each of the values in the xvals array. So you'll have two arrays at the end of the day. You'll have x1, an x array with 3 values in it, and an xvals array which will have 6 6 iterations, 3 of each, and we can always change the amount of duplications so you can get a converged solution as you move forward. But in this case 6 was probably the correct amount. It's something in the workshop for you to test. So just to verify these, of course, there are much more powerful methods available within Python and ease to solve these equations, and ease is probably the most straightforward of all, in that it is an equation solver. It's the engineering equation solver. So the way in which that's solved is just to type the equations in and solve them, and you should find the results are 1, 3 and 4. In Python, not particularly more complicated, just got to remember what libraries to use. So we import the numerical Python library as NP, so that rather than typing numpy all the time, we can just type NP. And from the scientific Python library, linear algebra, I'm going to import the solve. We then set up an array, and the array is simply the numbers of the coefficients of each of the 3 equations. I also need the array B, which is the other side, and this is a column vector. So now we have an array and a vector, and we just issue the solve command, and that essentially will invoke Gaussian elimination, and if it becomes unwielding, it'll use iterative methods behind the scenes. An alternative method is in Maxima, very simple in Maxima, in that we just literally type the equations in and then issue the solve command, equation 1, equation 2, equation 3, and then the float. Simplest of all, I guess, is Scilab, and MATLAB in this particular case, because it's built on for matrix laboratory type computations. That said, you still do need in the programming languages such as Python and Scilab to put these into a array format, the x equals b type format. But that aside, it's then a simple matter of doing the backslash, which invokes first of all Gaussian elimination and then any iterative method to speed the process up.